Nearly 100 kilometers of railway carved beneath one of the busiest cities on Earth, and almost nobody upstairs felt a thing. 8,000-ton machines. 10 brand new stations built while London kept working above them. 21 kilometers of twin tunnels under the city core alone. How was any of this even possible? And what really happens in the final phase almost nobody ever sees? Somewhere below the coffee shops, the bus stops, the millions of feet walking above, a 1,000-ton machine is getting ready to carve new tunnels beneath London. Almost nobody up there will ever see it. Each of these tunnel boring machines stretches roughly the length of 14 London buses parked end to end. 8 of them are built for this project. The math is not subtle. 21 kilometers of twin tunnels have to appear under a city that already has centuries of pipes, cables, sewers, and older subway lines packed into every cubic meter of dirt. Building a railway from scratch is one thing. Building one where a city already exists is another problem entirely. And here is what that problem looks like when it finally breaks through a concrete wall 28 meters underground. Elizabeth has just finished the first stretch of the longest tunnel drive of the project, 8.3 kilometers from East London toward Farringdon. The people upstairs in Canary Wharf had no idea a machine the weight of 280 taxis was about to punch through beneath them. Before any of these machines can be lowered into a shaft, somebody has to design 8 of them, each one tuned to the exact dirt they will meet. London does not have one type of ground under it. The west side is heavy clay. The east side is soft riverbed sediment left behind by the Thames over thousands of years. Under the river itself, the ground turns into chalk soaked with water. One machine cannot handle all 3, so the project uses 2 different designs. 6 of the machines are earth pressure balance types, used for the clay in the west and the sediment in the east. The other 2 are mix shield machines, built for the chalk under the Thames, where water is under constant pressure. Each machine has a rotating cutter head at the front, followed by trailers holding the mechanical and electrical gear. Together, they weigh around 1,000 tons and stretch about 148 meters. Each is expected to advance between 90 and 150 meters a week and land within a millimeter of where the plan says. A millimeter, across kilometers of underground travel through unpredictable ground. If you have worked on a tunnel boring machine crew, drop a comment. The manuals never quite explain the part where the dirt refuses to cooperate. Now walk inside one, and it stops feeling like a machine and starts feeling like an underground factory on rails. Precast concrete segments, each weighing about 3,000 kilograms. Arrive at the back on rail cars. 8 segments plus a key piece form a complete tunnel ring. At any moment, the crew is pushing forward against roughly 24 metric tons of reinforced concrete they just installed behind them. Every position is tracked in real time. This is a 10 million pound piece of equipment, and it knows exactly where it is every second. Before any of it can dig, somebody has to get a 550-ton machine 40 meters underground without dropping it. The lift required one of the largest cranes in Europe, working in perfect weather with light wind and no rain. That is roughly the weight of 280 London taxis dangling on a cable. Holy hell! One bad gust and the whole schedule slips by months. And even before the lift comes the assembly. The cutter head. The giant blue rotating disc that will grind through London clay has to be craned into place and mounted onto the shield body. Workers and cherry pickers guide it down millimeter by millimeter, a slow operation nobody upstairs will ever see. Then the moment nobody outside the project ever sees, the launch. Sophia begins her push from Plumstead toward North Woolwich, aimed at going under the River Thames. The 110-meter machine is expected to advance around 100 meters a week, installing concrete rings behind her as she goes. From the outside, it looks like a slow disappearance. From the inside, it is a 24-hour operation that will not stop. Curious what one of these machines looks like while it is actually running underground? This clip is from the Copenhagen Metro, using the same category of earth pressure balance machine. The cutter head presses forward, hydraulic cylinders push against the last ring, and a green guidance laser keeps everything aligned. Same physics, same discipline, different city. Behind every one of these machines is a team of about 20 people per shift, running 24 hours a day. Multiply that by 10 stations and 8 machines, and the human scale begins to show. The first Crossrail tunnel drive has just finished. A 6.8-kilometer run from Royal Oak to Farringdon, completed after 17 months underground. The route passed under Paddington, under mainline train tracks, under Hyde Park, and straight beneath the West End without disturbing a single restaurant reservation above. The team planned for around 100 meters of tunnel a week. Actual production climbed to peaks of 250 meters a week, a serious result for a machine grinding through central London clay. The dig produces its own problem. 1.1 million tons of excavated material had to go somewhere, so the project set up a chain. Spoil travels by mainline train to a transfer station downstream on the Thames, then loads onto ships bound for a nature reserve in Essex, where it expands wildlife habitat instead of piling up in a landfill. Meanwhile, 40 meters below the financial heart of the city, Elizabeth is inching forward at 5 millimeters per minute. That slow speed is deliberate. It protects the cutter head as it breaks through a concrete plug at Liverpool Street. Above, the City of London operates as usual. Below, dust mitigation misting bars are already spraying the tunnel eye seconds before the wall collapses inward. Not every part of the underground gets carved by a giant boring machine. At Whitechapel, the platform tunnels are dug using a technique called sprayed concrete lining, a slower, more surgical method for tight urban conditions where a full tunnel boring machine cannot fit. Because neighbors live right next door, all the surface support equipment sits inside an acoustic shed to allow 24-hour work without waking anyone up. The tunnels here run about 250 meters long each, matching platform length. The eastbound is longer to house a crossover chamber where trains can switch tracks. To speed up excavation of the passenger escalator shafts, the contractor brought in a modified German coal mining machine adapted for uphill tunneling. The operator stays in a safe position while the machine climbs. Digging upward while standing under thousands of tons of dirt is not a common problem to solve. These crews figured it out 30 meters below one of London's oldest neighborhoods. Then there is the station that had to be built inside a body of water. Canary Wharf Station sits in North Dock, a stretch of open water in the docklands. Before any concrete could be poured, the team had to build a steel dam using nearly 300 piles, then pump out roughly 100 million liters of water, equivalent to about 40 Olympic swimming pools worth. The piling used a silent hydraulic technique first developed in Japan, brought to the UK specifically to avoid rattling the high-rise buildings next door. Once the dock was dry, excavation began. 300,000 tons of material came out. 375,000 tons of concrete went in. The station box is roughly the size of the Canada Square Tower laid on its side. It was built top-down, without internal bracing, so heavy cranes and piling rigs could keep moving inside the excavation. Whoever calculated the concrete cure schedule on this deserves a very quiet office. Watch a single month of the project on time-lapse, and the true scale finally shows. Silvertown, Connaught Tunnel, Whitechapel, Liverpool Street, Farringdon, Paddington, all running at once. Cranes swing day and night. Track sections drop into place. Ticket halls take shape between weekends. The tunnels are only half the answer. The stations above them are the other half, and they are still empty shells. Two 240-meter platforms, 37 meters below street level, made of more than 500 precast concrete pieces manufactured 130 miles away near Sheffield. Each piece was trucked down, lowered through the main shaft, and fitted together underground like a very heavy jigsaw puzzle. The platforms are roughly twice the length of typical London Underground platforms, sized for the longer trains. Roughly 3/4 of the new route actually runs above ground once it leaves central London. That means the existing surface rail network had to be upgraded to accept the new trains. New tracks, ballast, and signaling. Over one Easter weekend, more than 3,000 workers were out on the line doing the physical integration. Once the concrete and steel is done, somebody has to decide what a passenger actually feels when they walk in. Are you serious? A design team spent months on light drum placement most commuters will glance at for 3 seconds? Tottenham Court Road sits under Soho in the West End, using color and open sightlines to move people through. Once the ring segments are locked in and the stations are structurally complete, there is a quiet phase almost nobody films: pouring the track bed. This is where the finished round tunnel gets a flat bottom that rails can eventually sit on. Concrete arrives by mixer truck through the city streets above, then gets pumped down through hoses into the formwork sitting around the rail supports. Workers spread and level the fresh pour by hand, working section by section under tunnel lighting. The process looks unglamorous. It is also punishing. If the surface is off by even a small margin over long distances, ride quality drops for passengers, wear on the rolling stock climbs sharply, and maintenance costs stack up for decades. A track bed is one of those quiet decisions that operators pay for, or profit from, every day the railway runs. Every rail on the Elizabeth line begins its life as a river of molten metal in a place like this. Iron ore feeds a furnace running at temperatures that would vaporize almost anything you could name. Ladles pour glowing steel from one vessel to another. Slabs come out red hot, get cooled by water sprays, and get rolled into coils. Same starting point, different destinations. Raw furnace steel is nowhere near clean enough to become a rail. It carries impurities that would crack under a passing train within months. The refining ladle is where operators fine-tune the chemistry: carbon, manganese, sulfur, to the exact recipe a modern rail demands. Skip this stage, and every kilometer of track you lay becomes a maintenance headache waiting to arrive. Now scale that discipline up to an entire industrial complex, and you get the sort of mill that supplies rails for national rail networks. Blast furnaces, oxygen converters, continuous casters, and rolling mills all sit on the same site. Blueprints get inspected under microscopes. Control rooms monitor process data on wall-to-wall screens. Laboratories run chemistry checks around the clock. The workflow is relentless because rail specifications are punishing. A steel bar destined to sit under train wheels at speed has to hit specific hardness numbers, specific fatigue resistance, and specific tolerances that most industrial products would consider paranoid. Miss any one of those, and you get cracks a few years later that nobody wants to explain to a safety inspector. The mill runs day and night in shifts. Historical footage cuts in showing the founding years, when the country first decided it needed heavy industry of its own. Rail was one of the earliest reasons to build a mill like this. And here is where the rail actually gets its shape. Rectangular steel blooms, each 4.5 to 8 meters long, arrive by train from the neighboring steel shop. Each bloom already has its chemistry documented: heat number, caster strand, position. Nothing anonymous. Every bar carries a paper trail. The blooms get reheated in a walking beam furnace running around 150 tons per hour, then blasted with 400 bars water jets to strip off scale. What comes next is a series of rolling stands that squeeze the rectangular bar into the familiar rail profile: head, web, and foot. Along the way, 4 laser sources and high-resolution cameras scan the cross-section on the fly, comparing the actual shape to the theoretical model. If a millimeter is off, the system flags it before the bar cools. The finished rails come off the mill in 108-meter lengths. For rails destined to carry high-speed traffic, an induction line reheats the running surface, and water sprays force cool it, hardening the top of the rail so wheels grind it slower over the decades. Then eddy current tests and ultrasonic pulses check for defects hiding inside the metal. Step into any serious heavy metal shop and the same rules apply. Timing, temperature, and the sort of teamwork that does not tolerate a single distracted worker. Molten iron gets transported by overhead crane in a ladle glowing at temperatures far past what human skin could survive nearby. The pour into the mold has to happen within a narrow window before the metal starts to cool and lose flow. Everything is choreographed by voice, hand signal, and years of shop floor instinct. Nobody rushes. Nobody stops. A rail mill runs on the same nerves as a foundry. Different end product, same respect for what molten metal does when you look away. Once the rails leave the mill in 108-meter lengths, they still have to make it into a live tunnel and lock into place with millimeter accuracy. That job comes with its own set of surprises. Meet the finished 108-meter rails going into place, one shift at a time, deep under the streets of central London. Roughly 1,200 people are working around the clock to fit out 26 miles of tunnel with permanent track. 5 different track designs are being installed across the network. Around 80% is standard slab track, sleepers embedded in a poured concrete bed. The other 20% includes direct fixed track through the Connaught Tunnel, 2 types of floating slab, and high attenuation sleepers for extra sound damping. Mobile gantry cranes distribute rail and sleepers off the back of the delivery train. Crews align the track to its exact horizontal and vertical position, then pour concrete around it. Because there is no batching plant underground, concrete arrives in shuttle wagons and gets pumped through a pipeline running back down the tunnel. A rail off by a couple of millimeters over kilometers of tunnel is a rail that shakes the whole train. Now stand 35 meters under the Barbican Theater, a concert hall where the audience really does not want to hear a train. So the track slab here is built on heavy-duty springs. 48 slabs, jacked up on springs, absorb vibration before it ever reaches the ceiling above. Ballast works fine for old freight lines. It does not work when trains hit 250 kilometers per hour inside a tunnel. The rocks vibrate, drift, and turn into a maintenance nightmare. So the modern answer is slab track, a continuous concrete pathway with the rails locked directly to it. Here, trucks deliver concrete for the base layer non-stop. A laser system guides drivers along the narrow tunnel shelf so nothing slips into the void. A paving machine positions itself using 2 total stations and lays a horizontal base that adapts to curves by adjusting elevation on the fly. Meanwhile, weeks earlier and hundreds of kilometers away, precast track slabs are being cast in a factory. Workers place pre-stressed steel and reinforcement in molds. Vibration motors kick out air bubbles. Automated screeds finish the surface with grade C45/55 concrete. The tunnel needs 2,896 of these plates. Each one gets a unique barcode. If you have watched a slab track crew work through the night, has anyone here seen the millimeter tolerance actually hit on the first try? Genuinely curious what that looks like from the pit. Cured plates get vacuum lifted, transported by truck, and installed in the tunnel with adjustment tolerances tighter than 1 millimeter. The trick that makes ballastless track work is buried inside each concrete slab. An elastomeric layer sits between the rail and the concrete, cutting structure-borne sound and preventing stress cracks from forming under repeated wheel loads. Precast in factory conditions and shipped to site, the slabs arrive at roughly 5.16 by 2.4 meters, ready to drop into place. The goal is simple: finish more work in the factory and leave as little as possible to chance in the field. Installation moves quickly because the heavy work already happened indoors, under controlled temperature and humidity. Cranes position each plate to within half a centimeter of the design line. Self-compacting concrete, poured without vibration, locks the plate to the base without disturbing the fine adjustments made moments earlier. If a plate gets damaged, a 50-meter section can be replaced in about 10 hours instead of shutting the entire line down for a full week of repair work. Then somebody asked the obvious question: do we really need concrete under the concrete? A project near Stuttgart tried replacing the concrete base layer with low-temperature asphalt containing recycled content. Test institutes ran shear bond strength tests. Cores passed. Cheaper base, faster laydown, lower emissions. The core rail system stays exactly the same. Rails do not arrive on site as a continuous ribbon. They come in sections that have to be fused together end to end, so trains do not clack over gaps. Flash butt welding runs electric current across the two rail, ends until they glow, then presses them together to form a joint stronger than the parent metal. On tight, high-speed lines, mobile rigs lift the rail into position without touching the surrounding track. And every branching point where two tracks split into a Y needs a specialized piece of hardware called a turnout, the movable rail that lets trains change tracks. These get pre-assembled at a factory, then delivered by rail on custom wagons that clamp and cushion the whole assembly. On arrival, cranes lift the turnout straight from the wagon onto the prepared base. Even brand new rails do not stay smooth on their own. As wheels roll over the running surface, tiny imperfections turn into ripples that make trains vibrate. High-speed grinding rigs run along the track with rotating grinding wheels, shaving off microscopic defects before they grow. Sparks fly out sideways in a wide arc. The rail comes out mirror smooth. Now imagine doing all of this on a line where trains still run at 230 kilometers per hour the moment your shift ends. On the Hamburg to Berlin corridor, crews swap out worn rails 180 meters at a time. Elastic sleeper pads protect the concrete ties from being crushed under high-speed loads. Rollers slip under the rail every 15 sleepers because heat during welding preheat makes the metal expand several centimeters. More than 3,300 pads get installed per kilometer. Everything runs on a Swiss watch timetable, day and night. Track and rail alone still do not run a train. Somebody has to bring the power. Once the track is down, the tunnel walls suddenly look empty. No cables, no lighting, no signaling, no overhead power. All of that has to hang off brackets bolted into the concrete tunnel lining, which means around 250,000 to 300,000 holes have to be drilled with millimeter precision across 42 kilometers of tunnel. A purpose-built drilling rig, the first of its kind anywhere, handles the job. Before the physical drilling starts, a 3D scanner runs down the tunnel, taking measurements at tiny increments. Software then maps every hole position onto the exact geometry of the scanned rings. The rig itself uses guide rollers to center itself against the tunnel lining, so every drill bit strikes perpendicular to the concrete. Output runs 200 to 250 meters per shift. The old method. Surveyors marking holes by hand, drillers reaching into the wall with handheld tools, is why railways used to take longer. Once brackets are drilled in, the copper wire that will feed the trains has to be strung across every meter of route without a snag. Specialized rigs with elevated work platforms roll along the track, spooling out contact wire under carefully controlled tension. Get the tension wrong, and the wire sags in summer heat or snaps in winter cold. By autumn 2014, tunneling was almost 90% done. And that was when the real complications started showing up. Two remaining machines had launched from Whitechapel heading west, aiming to close the last 6 kilometers of running tunnel. Meanwhile, station construction was taking shape across 10 new sites. At Paddington, the tunnel top had just been breached and connected to the future station box. At Tottenham Court Road and Bond Street, excavation was finished, and the crews were laying concrete foundations for platforms and ticket halls. At Whitechapel, the uphill excavator finished carving out escalator shafts, the first machine ever used in the UK to tunnel from the bottom up. The tricky part was that all of this ran in parallel. Tunneling in one zone, station fit-out in another, surface works by the network operator in a third. The scheduling document alone probably ran longer than the average novel. Then came the moment the project team had been driving toward for 4 years. The last tunnel boring machine punched through at Farringdon. All 42 kilometers of running tunnel were now linked from Paddington in the west to Woolwich in the east. Over 10,000 workers had contributed to the effort, including 446 apprentices trained on the project. Around 7 million tons of excavated earth had come out during tunneling. Roughly 98% of it was reused, most famously to build up a wildlife habitat on Wallacea Island in Essex, where bird populations moved in almost immediately. With the tunnels done, focus shifted to fitting them out. New teams brought in specially designed machines to install track, communications, power systems, and everything else needed to turn concrete tubes into a working railway. The station structures were around 2/3 complete. The project was 65% finished overall. By 2019, the tunnels had rails, brackets, cables, and overhead wires, and testing was underway. 2 new trains were running close together in the central tunnels, an essential step for safety certification. The signaling software was maturing enough to verify against real train movements. Trial running, a phase where the whole system runs as if it were open, was targeted for early 2020. Then came the final phase almost nobody outside the industry ever hears about. Testing 8 trains at once, running 16 hours a day on a mimicked timetable. Signal software talks to platform screen doors. Route setting handles trains automatically across the fringes. Maintenance crews inspect the infrastructure between runs. This is what a railway looks like the moment before a real passenger walks in. Nearly 100 kilometers of railway carved beneath a city that never stops moving. And by the time the first passenger boarded, most of them still had no idea what happened below their feet. 8 tunnel boring machines, 10 new stations, 42 kilometers of running tunnel, 7 million tons of earth relocated to build bird habitats instead of landfill. Steel rails traced back to mills in Spain, Turkey, and beyond. The argument underground engineers keep circling back to is worth thinking about. Some say projects like this prove big infrastructure still delivers. Others point to the delays and cost overruns. Honestly, projects like this feel harder to build than ever. Not because the engineering is impossible, but because getting them approved is. Let us know what you think. If the world beneath the streets is your kind of story, the subscribe button keeps the next one coming your way. See you. Take care.